who invented it. So it is known as the Schering Bridge, and it is used for the measurement of capacitance by comparing it with a standard capacitor. Now in this bridge, the capacitance of the capacitor which we are measuring, this capacitor, it is an imperfect capacitor. Means this capacitor will have dielectric losses in it. So imperfect capacitor, their capacitance can be measured with the help of this Schering bridge. Now Schering bridge, it is a type of an alternating current bridge. So it will consist of 4 arms. The bridge network, it consists of always the 4 arms AB, BC, CD and DA. In these 4 arms, we are having the 4 impedances. Impedances are the combination of a resistor or a capacitor or an inductor. So these impedances in the 4 arms, they can be a combination of resistor, capacitor or an inductor. It can be a series or it can be a parallel combination, or it can only be a capacitor or only an inductor or only an resistor also. Now out of these 4 impedances, that is Z1, Z2, Z3 and Z4, the Z1 is our unknown impedance. Means the value of the electrical parameter which we want to measure, that will be connected in the Z1, that is AB arm. Okay. Now here we are measuring the value of the capacitance of a capacitor. So unknown impedance will be our capacitor, and Z2, Z3, Z4, it can be a resistor only, or it can be an inductor, or it can be a capacitor, or combination of these threes. Okay. Now the value of these Z2, Z3 and Z4, it will be known to us. So we can measure the value of this unknown variable in terms of these known variables using this bridge. Now other than these 4 arms, the alternating current bridges, they also have a detector which is used to obtain the balance condition for the bridge. Okay, balance condition means when the detector, it will give us the null deflection, then the 4 arms, the impedances in the 4 arms, they will be balanced and they can be described by a balance equation, which is Z1 Z4 is equals to Z2 Z3. So when the bridge is balanced, this is the balance equation for the bridge, and using this equation we can find out the value of the unknown impedance. You can see Z1 will be equals to Z2 Z3 upon Z4. So we will simply put the value of the impedances in this equation and can find out the unknown impedance through this bridge. Now this was the work of the detector. Detector was used to obtain the null condition or to obtain the balance of the alternating current bridge. We are also having an AC voltage source, and that voltage source gives the power supply to the bridge network. So the alternating current bridge, it will consist of 3 things. We will have the 4 arms in which we are having the impedances. Then we have the detector and an AC voltage source. So let us see the circuit diagram for this Schering bridge. So this is the circuit diagram for the Schering bridge. In this bridge you can see we are having the four arms A, B, BC, CD and DA. And in these arms we are having the impedances. This impedance is the Z1, this is Z2, this is Z3 and this is Z4. You can see that the impedances, they are the combination of the capacitor and the resistances. Z1 is the combination of the capacitor C1, the unknown capacitor, and this capacitor is having a dielectric loss component which is represented by this resistance R1. Then Z3 is a non-inductive resistance R3. This Z2, it is a standard capacitor. This standard capacitor is loss free. There are no dielectric losses in it. So we have not connected any resistance which is representing the loss component. So it is a standard capacitor. Then Z4, it is a parallel combination of a capacitor, variable capacitor C4 and a variable resistance R4. So this is the circuit diagram. In this you can see we are having a detector also in between B and D, and in between A and C we are having the AC voltage source. This is the symbol for the AC voltage source, and this voltage source is providing the EMF E to the whole circuit. Now the voltage drop across the AB arm, it will be even. Across AD it will be E2. Across BC it is E3, and across CD it is E4. And I1, I2, I3, I4, they are the respective currents in the arms. So let's see that what is the configuration of this Schering bridge. How we can get the value of the impedances Z1, Z2, Z3 and Z4. So arm AB was the unknown capacitance C1 connected in series with the resistance small r1. So our impedance Z1 will be equal to the series combination R1 plus, when we are representing the capacitance, then the capacitance is represented by the capacitive reactance Xc, and the value of Xc is what? 1 upon j omega C. So here we are having the value of capacitance as C1. So Xc will be 1 upon j omega C1. So here the resistance is R1 and the capacitance value is 1 upon j omega C1. Okay. Next we are having the arm BC. Arm BC is having the known non-inductive resistance R3. So our impedance Z3 will be equals to the resistance R3 only. Then we are having the arm CD, which is the parallel combination of a variable capacitor and a variable resistance. So it is a parallel combination. So if we talk about the parallel combination of a capacitor and resistor, this is the resistor. Resistor is R and capacitance is Xc again. So if we find out the equivalent impedance, it will be 1 by Z equals to 1 by R plus 1 by Xc. So 1 by Z is equal to 1 by R plus Xc is what? 1 upon j omega C. So we will write here j omega C. So 1 by Z is equals to 1 by R, or we can say 1 plus j omega C R upon R. So it is the reciprocal. So impedance will be what? R upon 1 plus j omega CR. Now here we are having the R4 and C4. So our impedance Z4 will become R4 upon 1 plus j omega C4 R4. Okay. Just putting the value of C4 as C as C4 and R is replaced by R4. So our formula is now R4 upon 1 plus j omega C4 R4. Okay. Next we are having the arm DA. Now arm DA, it is the capacitor, standard capacitor C2, which is loss free. Okay. So the value of this impedance will be Z2 equals to 1 upon j omega C2. So we have got the value of all the four impedances Z1, Z2, Z3 and Z4. Now we are going to put the value of these impedances in our balance equation Z1, Z4 equals to Z2, Z3. This is the balance equation for an alternating current bridge. The value of Z1 is small r1 plus 1 upon j omega C1. Z4 is what? R4 upon 1 plus j omega C4 R4. Z2 is 1 upon j omega C2 and Z3 is R3. Okay, we have just put the value of all the impedances in this balance equation. Let us simplify this equation. R1 multiply with this, or we can say if we put this denominator part, that is 1 plus j omega C4 R4, if we bring it to the right hand side, it will be R3 upon j omega C2 multiplied with this 1 plus j omega C4 R4. We have just bring this denominator part to the right hand side. So we have multiplied this R4 inside the bracket and this term inside the bracket. So we have got R1 R4 plus R4 upon j omega C1. This is on the left hand side, and in the right hand side we have got R3 upon j omega C2 plus j omega C4 R4 R3 upon j omega C2. J omega, they will be cancelled. Okay, and we know that 1 upon j can be written as minus of j. Okay, so we have, instead of 1 by j, we will write minus of j. Here also we are having 1 by j, so we will write it as minus of j R3 upon omega C2. J omega is already cancelled, so we are left with C4 R3 R4 upon C2. Now in this equation we are having imaginary terms also and real part terms also. So we are going to equate the real parts of the equation and the imaginary parts of the equation separately. This is the real part R1 R4, and this is also the real part. So C4 upon C2 R3 R4. So when we are equating the real parts, we are getting this equation. R4 and R4 will be cancelled. So the value of small r1 will be C4 by C2 and then multiplied with R3. This is the value of small r1. If we equate the imaginary parts, that is the part having the j omega terms, so we will get minus of j r4 upon omega c1 equals to minus of j r3 upon omega c2. J minus sign omega, they will be cancelled. So we will get the value of the capacitance C1 as R3 by R4 into C2. So our unknown impedance was Z1. Z1 is equals to R1 plus 1 upon J omega C1. So we have got the value of R1 also and C1 also. So we can put it in this and we can get the value of the unknown impedance. Now if we equate the imaginary parts, so imaginary parts are those parts having J omega terms. So this they will be equated minus J R4 upon omega C1 equals to minus J R3 upon omega C2. Minus J and omega, they will be cancelled because they are present on both sides of the equation. So we will get the value of the capacitance C1 as R4 upon R3 into C2. This is the value of the capacitance C1. Now, so by equating the real parts, we have got the value of the small r1, which is the dielectric loss component of the capacitor, and by equating the imaginary parts, we have got the value of the capacitance. You can see we have got the value of these unknown impedances or the unknown variables in terms of the known variables. Now the unknown impedance Z1 was R1 plus 1 upon J omega C1. We have got the value of R1 also and C1 also. So we can put these values in this equation and we can calculate the unknown impedance. So this is how we can measure the value of the capacitance by using the Schering bridge. Now instead of other than this capacitance, this Schering bridge, it can also measure another factor which is called the dissipation factor. This dissipation factor is calculated for the storage elements like for the capacitor and for the inductor, and it represents the loss component in the capacitors. Okay, so dissipation factor, it is defined as and also it is the reciprocal of the quality factor. Quality factor, it defines the energy stored in the element. So it gives us about the information about the goodness or the quality of the element. Okay, and this dissipation factor, it is the reciprocal of the quality factor, and it is defined as the tangent of the loss angle. So if we denote this dissipation factor by D1, and it will be equal to tangent tan of the loss angle, that is del 1. Okay, and this is equal to omega C1 small r1. Now we have already got the value of the capacitance and the resistance C1 and R1. So just putting the value of C1 and R1 in this equation, we will get D1 equals to omega. C1 is what? R4 upon R3 into C2. R1 is what? C4 upon C2 into R3. C2, C2 cancel, R3 and R3 cancel. So the value of the dissipation factor is omega R3 C4. So this is the dissipation factor in the capacitor C1. Okay. So using this Schering bridge, we can not only find out the the capacitance, the unknown capacitance, we can also find out the dissipation factor for that capacitor. Now coming to the phasor diagram of the Schering bridge. Now phasor diagram, it represents the phasors or the vectors of the currents and the voltages across the bridge network. So this was the circuit diagram. Now in this circuit diagram you can see that we have different voltage drop across the four arms E1, E2, E3 and E4. Also we are having voltage drop across each element also. So what is the relationship between the voltage and the current across these elements? That will be represented in the phasor diagram. So before drawing the phasor diagram, one concept should be clear to you, that what is the relationship between the voltage and current across a resistor and across a capacitor. Now across a resistor, the voltage and the current, they are in phase with each other. Okay, they are in same phase. So they will be drawn on the same line. If we are drawing the voltage, then current will be drawn on the same line. And if we talk about the capacitor, in case of a capacitor, see the voltage, it lags the current by 90 degree. So if current is drawn as the straight line, so voltage will be 90 degree behind it. So this concept will be used to draw the phasor diagram. So in the phasor diagram, we will take a reference current, and across that phasor, reference phasor, we are going to draw the other phasors or other vectors. So here we will take the current I1 as our reference phasor, I1 current. Now taking the first term. In the first term, we are having a capacitor also and we are having a resistance also. So across the capacitor, the voltage drop will be I1 upon j omega C1. This is the voltage drop, and current is what? I1. I1 we have already drawn. So 90 degree lagging behind it will be the voltage across the capacitor. And if we talk about the resistance, so resistance is what? I1 small r1. Okay, so the voltage and the current, they will be in same phase with each other. So in the first term we are having the capacitance, so the voltage across this capacitance, it is going to lag the current by 90 degree. So at a 90 degree lagging, we have drawn the voltage for it. Now coming to the other element, we are having the resistance. So the voltage across this resistance will be I1 R1. Okay, so I1 R1 will be in same phase with this current I1. Okay, so I1 is here, I1 R1 will be drawn on the same line. Okay, and when we are going to take the resultant of these two vectors, we will get the voltage E2, because E1, because E1 is equal to the sum of the voltage drop across the capacitor also and across the resistance. So across the capacitor we were having I1 upon j omega C1, and across the resistance we are having I1 small r1. So their sum will be equal to the voltage E1. Okay, so here if we extend these two phasors, we will get the voltage E1. Now when the bridge is balanced, then the detector is going to give us the null deflection, and the detector will give us null deflection. It means that the potential at point B and D is equal. It means the voltage drop E1 will be equals to the voltage drop E2. Okay, and here we have drawn the vector for the even voltage. So E1 will be going to equal to E2. Okay, and this E2 voltage drop, it is the voltage drop across the capacitor, this C2, and this voltage drop is I2 upon j omega C2. So I2 upon j omega C2, it will be equals to this, the voltage drop E2. Now current across this capacitor is I2 and voltage drop is I2 upon j omega C2. So these two, they will be in a 90-degree difference with each other. Here we have drawn the voltage, so current will be 90-degree ahead of this. Okay, so 90-degree angle we are going to draw the current I2. So this angle is 90-degree, also this angle is 90-degree. Okay, current was I1 j omega C1 lagging behind it. Current is I2 upon j omega C2 90-degree lagging behind it. Now let's come to the right hand side part. Now in the right hand side we are having the voltage drop across this resistance R3 as I3 R3. Okay, but when no current is flowing through this detector in this arm, no current is flowing, it means that this I1 current will be equal to the current I3. I1 will be equal to I3, and also this I2 will be equals to I4. I2 will be equals to I4. Also this E1 was equal to E2, so E3 will be equals to E4. This is this condition. Now E3 is what? I3 R3, or we can write it as I1 R3. Okay, so I1 is here, so I1 R3 will also be on the same line. So here we are writing the current or the voltage E3, which is I1 R3. We can write it as I3 R3 also, but I3 and I1 are equal, so we are writing here I1 R3. Now voltage drop E3 is equals to E4. E4 is the voltage drop across this capacitor and resistor. Now when this capacitor and resistor, they are in parallel combination, so voltage will be equal on it. So E4 will be equal to the voltage drop across this capacitor also and across this resistance also. Across this capacitor, if we suppose that the current is IC, and across this resistance, if we suppose that current is IR. Okay, so voltage drop across capacitor will be IC upon j omega C4, and the voltage drop across this resistance will be IR and R4. Okay, and that will be equal to the E4, or we can say it is equal to E3. So E3 we have drawn here, so it will be equal to IC upon j omega C4. Also it is equal to IR R4. Okay, now IR R4, it was the voltage drop across this resistance. So voltage drop and the current, they will be in same phase with each other. Voltage drop we have already drawn IR R4. So IR will be on the same line. Okay, and the current, or we can say the voltage across this capacitor is IC upon j omega C4, and current is what? IC. So IC and this voltage drop, they will be in 90-degree difference with each other. Voltage is going to lag the current by 90-degree. So voltage is drawn on this line, so current is 90-degree ahead of it. That means this is the current across the capacitor. So resistance, current and voltage, they are in phase with each other, and capacitor voltage and current, they are 90-degree difference with each other. Okay. Now this as we have said that this I2 current is also equal to I4. I2 is equal to I4. No current is flowing in this arm. So I4 is what? IC plus IR. Or we can say IC plus IR is equals to I2. So I2 is here. If we extend this IC and IR, we will get this current I2. Okay. Now the total EMF provided by the voltage source is E. So E is equal to the sum of E1 plus E3, or we can say it is the sum of E2 plus E4. So if we extend these vectors E2 and this E3, we will get our resultant EMF or total EMF E, and this is equal to E1 plus E3, or we can say it is equal to E2 plus E4. Okay. So this is the phasor diagram of the Schering bridge, in which the relationship between the vectors or the phasors of the currents and voltages across each element present in the network, that is shown. You can see we have considered all the capacitors and resistances, the voltage drop across them and the current across them, and we have drawn their relationship in this phasor diagram. So in this video we studied the measurement of capacitance using the Schering bridge. In this video we studied the circuit diagram, the balance equation, how we are getting the value of the unknown capacitance, and dissipation factor we also studied that how it can be calculated, and in the last we studied the phasor diagram for the Schering bridge. So I hope that this topic is clear to you. Thank you.